time, we went through all the different ways to represent the different forces we see, and you have all the information you need for that for the rest of the class. I think that's right. Definitely for the next long time. I think for the whole class. Before I get back into this stuff, does anyone have any homework questions you want me to go over? It's pretty easy and quick to go over them, so if you want me to do any, I'd have no problem doing that. Let's do one more example problem with a free body diagram just to sort of remind you how this stuff all works. And then we'll get into going from the free body diagram to doing calculations in Newton's second law. Okay, so let's say that we have a ramp there and a ramp at a different angle here, and a pulley in the middle. And let's say we have a block here. And this block has a mass of 5 kilograms. And then a rolling cart on the other side. They're connected by a cable that goes over the pulley. And let's say this rolling cart has a mass of 1 kilogram. And there's friction between the 5 kilogram block and the incline. And the coefficient of friction between those is 0.2. And we want to draw a free body diagram of each body. Okay, well, I'm going to start with the 5 kilogram. So I'm going to draw it at the angle that it's at. There's a weight force that's equal to 5 times 9.81. So this is 49.05 newtons. And now I'm going around the boundary looking for places where the surroundings contact the boundary. The first place that I see, I guess I'm sort of starting at the bottom, is the contact with the ramp. So that is going to be a pair of two forces that always happen. Oh, and I need to give you some information that I hadn't yet. This is the direction of motion of these things. Remember that you need to know, if you're going to put in friction forces, you need to know the direction of the velocity of the object at the instant. So at this instant, they're sliding to the right. Okay, so down at the bottom, the contact with the ramp applies two forces: a friction force that's in the opposite direction of the velocity, and a normal force that's the contact between the ramp and the object. So the normal force, that's a pushing force. And the rules of a pushing force are toward the chosen body and perpendicular to the surface. So that's going to be like this, and I'll give it a variable name n. And the other force in this pair is the friction force. That's going to be opposite the direction of the velocity vector, so this way. And the magnitude of that force is going to be the coefficient times that pushing force, whatever that is. Okay? Any questions about those contacts with the ground? And now if I keep going around, there's one more place the surroundings contact the boundary. That's where the cable contacts. And so the rules say that force is away from the body, parallel to the cable. And I'll give that the magnitude T for tension. And now I'll go to a free body diagram of the 1 kilogram. So there's the closed outline of the body. The weight force is 1 times 9.81, so that's 9.81 newtons. There's a contact with the ramp, so that's toward the chosen body, perpendicular to the surface. Is there any reason that that pushing force would have the same magnitude as this pushing force? These are totally different things with totally different weights. The ground has to push harder to keep the 5 kilogram mass from accelerating. So I have to give this a different variable name. So I'm going to call this one N1, I guess, for 1 kilogram. Okay. That's just another way of, like I could call it X or Q or something, but I'm just calling it N with a subscript. And then the last thing is there's contact between the cable and the surface. So that force is away from the body, parallel to the cable. And is there any reason that the magnitude of that force is the same as the cable force on the other one? Yeah, it's the same cable. So as long as it's the same cable and anything it goes through is pulleys, this is the same as this one. I want to point out one thing about the friction forces. So why is it just intuitively that, did I talk about this last time? I don't think so. Why is it that the friction force is multiplied, is, a constant multiplied by how hard the surface is pushing on this? Does that make sense? So let me give you an example. So think about the friction force of this as it slides along the table, okay? Right now, this isn't super heavy, so the table doesn't have to push very hard. It's not a very big force pushing this and the surface together to keep it from sinking into the table, okay? It's just not a very big force because it's not very heavy. And the friction force, as you would imagine, is not that big. It's not too hard for me to push this way, right? But I could increase the pushing force that the table has to apply to this by pushing, like putting all my weight on top of this. Now the table is applying a really big force up. Does that part make sense, that's increasing that normal force? And intuitively, if I put all my weight on this, you can imagine that it's going to be a lot harder to push this along the surface, okay? So the thing is that the amount of friction that's applied goes up as that pushing force with the surface goes up. And that's what it does to multiply that coefficient times that normal force, that pushing force. Okay. So remember that N, when you multiply this coefficient of friction times N, that's not newtons, that's multiplying it by a variable. Okay. So now what I'm going to do is just go through some steps for using Newton's second law, and then we're just going to get into a bunch of example problems and the kind of things that you can calculate using Newton's second law. So the first step always when you're, yeah. Yeah, so when I put wheels on something, I always mean that as kind of like a way to say there's no friction. But I also could have drawn it as a box and just said there's no friction between those contacts. So like on a test or something, if you're ever unclear about whether there's supposed to be friction, feel free to come ask about it. That's not supposed to be like a tricky thing or anything, you know. But yeah, anytime I draw wheels, it's kind of a shorthand way for me to say there's no friction there. Okay, so if you're going to use Newton's second law, the first thing you always have to do is draw a free body diagram of your chosen object. Second, determine whether the object can move along the x or y axis. Or, you know, there'll be some cases where the thing isn't free to move at all, it's held in place. If it moves along the x-axis, then you're going to write your acceleration vector as a0, because the only possible acceleration is an x component. If it's free to move along the y-axis, then your acceleration vector is 0a. And if it's fixed, then there's no acceleration. One thing I want to point out is things can have accelerations in the positive or negative x direction, or the positive or negative y direction. But we don't have to make that determination before we do the calculations. Those signs are always going to come out in the calculation. Okay, so we don't have to think, okay, it's moving along the x-axis in the negative direction. All we have to say is it's moving along x or it's moving along y. Okay. And then the last step is put your forces and your acceleration into Newton's second law and use those equations to solve for the variables. So let me just start doing a bunch of problems. So the first one, let's say that there's a mass of 20 kilograms and it's attached to the ceiling by a cable. And then besides the weight of this object, we're also pulling down with an additional force of 40 newtons. And we want to know what's the force vector applied to the mass by the cable. So I gave you 3 steps to do. The first one is to draw a free body diagram of the body. Then we have to figure out what we know about the acceleration, and then we'll put it into Newton's second law. So first I'm going to do the free body diagram of the mass. The weight force is down. The magnitude is 20 times 9.81. So that's 196.2 newtons down. Then we're told that there's an additional 40 newtons down there. And then if we go around the boundary, the only other place where our boundary makes contact with the surroundings is at the cable. And so that force is away from the body, parallel to the cable. So those are all the forces that are going to go into Newton's second law, on the left side of Newton's second law. And now the second step of this process is figure out what we know about the acceleration. This is just hanging there. So what's the acceleration going to be? 0. Anybody have any questions about that? So the acceleration is 0 anytime the velocity doesn't change. This velocity stays 0 the whole time, and so the acceleration is 0. And so now I'm going to go into Newton's second law. And any force that shows up in the free body diagram has to go in Newton's second law. That force T, what's that as a vector? What are the components of that force T? If I'm using, the usual coordinate system like this. If it helps, you can always, write it down with the tail at the origin and figure out what the coordinates of the head would be. So what are the coordinates of the head of this vector?
0 something?
Yeah, 0 something, and the something is t. Whatever that t is, that's the coordinates. Any questions about that? So we know that it's all in the positive y direction, and the height is t. Yes?
So is it the length of the string holding the object?
It's actually how hard the string is being pulled. It's the magnitude of the force. And we don't know what that is, so we're going to have to calculate that. So that's why there's a tension in there. So the first force is 0t. Then what about that weight force, the 196.2 force? What's that as vector components?
Center of mass.
So this one, I'm going to draw the coordinate system again. And here's the vector. And it has a length of 196.2. So what are the coordinates of the head of this vector?
0, 1, 96.2.
Yep, negative 196.2. You see that? And then the last one is this 40. So this vector has a length of 40 in the negative y direction. So what's that force vector? What are the components? 0, negative 40. Okay? And Newton's second law, now there were 3 forces in the free body diagram, and we have our 3 forces here. Now Newton's second law says this is equal to the mass, which was 20 kilograms, times the acceleration vector, which we know is 0, 0 because it's not moving. And so this gives us 2 equations. The x equation says 0 plus 0 plus 0 is equal to 20 times 0? Well, that doesn't help at all. So this, we weren't able to solve any variables with that one. But the y equation says t minus 196.2 minus 40 is equal to 20 times 0. And so t minus 236.2 is equal to 0. And so t, now we just have to do the algebra, is equal to 236.2 newtons. And so what that tells us is if we have a rope that can't withstand a tension of 236.2 newtons, this rope is going to break. Okay. Now, I didn't exactly ask for the tension in the cable. I asked for a little more than that. I asked for the force vector that's applied to this by the cable. So notice that the force vector is this thing. Okay. So now that we have that variable value, we can just plug it back into here. And it says that the force on the block by the cable is equal to 0t. We know what t is, sorry. 236.2. And this is in newtons. And if you wanted to visualize that force, that's in the positive y direction. So you could also think of this as an upward force of 236.2 newtons.
Would you accept both of those, Anthony?
Yeah, either one of those is fine. Any questions about that? I think as we just keep going through these, it'll get more clear. So this time, let's say that there's a rolling cart on a horizontal surface. And this cart has a mass of 10 kilograms. And let's say we know that a 20 Newton force is applied this way. And a 10 Newton force is applied this way. And a downward force of 50 newtons is applied at the top. And we want to calculate the acceleration vector of the cart. Okay, so what's the first step in this problem?
Free body diagram.
Yep, perfect. Free body diagram. There is a weight of 10 times 9.81, so 98.1 newtons. And then I'll just put in all the stuff that we're given. So we have a 20 Newton force that way, a 10 Newton force that way, and a 50 Newton force that way. And now go around the boundary and look for any other place that the surroundings contact the boundary. There is one place. Where's that? The wheels, and that's a pushing force. So the rules say that force is toward the body, perpendicular to the surface, so like that. And I'll give that the name N. Let's calculate one more thing here too. So let's say part A is we're trying to calculate that acceleration. And for part B, let's calculate the force vector on the wheels by the ground. Okay, well, we know we're done with the free body diagram because we have a representation for the weight and we have a representation for every contact between the surroundings and the surface. So then you know you're done. Now we have to think about the acceleration. Is this thing free to move along the x direction or the y direction? Or neither? X, right. So I'm going to just write this as A0. We know that, like, for it to have a y acceleration, it would have to be able to sink into the surface or jump off the surface, and we know that's not happening. It's just rolling side to side. And now the last step is to go to Newton's second law. So one by one, let's go through these forces. We have 20 newtons acting in the positive x direction. So what are the components of that force vector? 20, 0. Yep, perfect. We have 50 newtons in the negative y direction. So what are the components of that vector?
0, -50.
Yeah, perfect. 0, -50. We have a weight force in the negative y direction. So what are those components?
0, -1.
Yep, 0, -98.1. Then we have the normal force in the positive y direction. What's that one?
And 0.
It's y, so it's 0n. Yep. And then this one has a lot of forces on it. The last one is that 10 Newton force in the negative x direction. So what are those components? -10, 0. Yep. And all of these forces are equal to the mass times the acceleration, which we already figured out is A0. And so now I can break this up into the x equation and the y equation. The x equation says 20 plus 0 plus 0 plus 0 minus 10 is equal to 10 times a. And so this comes out to say that 10 is equal to 10a, and solve for a, and you get a is equal to 10 meters per, no, 1 meter per second squared. Okay. We want the acceleration vector. Well, we already knew that the acceleration vector was a0. All we had to do was, we just had to figure out what a was. Now that we know that, we can plug it in here. Okay? So the acceleration vector is 1, 0, or to visualize it, that's in the positive x direction. So it's an acceleration this way of 1 meter per second squared. Any questions about finding that acceleration vector? So now we'll go to the second equation, the y equation. And that says 0, minus 50, minus 98.1, plus n, plus 0 is equal to 10 times 0. So that says negative 148.1 plus n is equal to 0. Solve that, and you get that n is equal to 148.1 newtons. Okay, again, now we've solved for this variable, but what we want is that force vector that's applied by the ground. But you already have all of your force vectors defined in Newton's second law. So this is the one we want. And so now we just have to plug n into that. And we get that the force on the cart by the ground is 0, 148.1. Or in other words, it's in the positive y direction with a magnitude of 148.1. Any questions about that? Yeah. For some problems you can, but I think it's a better idea to just do the calculations because otherwise you have to remember a bunch of rules for when that's true and when it's not true. We're going to see that when things are on inclines or, when things are on inclines, I guess is the one time where it's going to come up that it's not equal and opposite like that. But it's pretty easy to see once you write out the Newton's law equation for that component that, to see how it's going to work. Any other questions right now? Okay. Let's do one with friction. So let's say we have a horizontal surface and a block of 1 kilogram. Well, let's make it 2 kilograms. And let's say there's a horizontal force of 5 newtons. And a force pushing down of 1 newton. And let's say that the direction of motion is this way. And the coefficient of friction is 0.1. So we want to calculate the acceleration vector. And let's also calculate the force vector applied to the block by the ground. The first step is a free body diagram. We have a weight force of 2 times 9.81, so 19.62. Then we have these two given forces, 1 Newton going down, 5 Newtons going to the left. And now the only place where the surroundings contact the boundary is at the ground. And so this is going to happen in 2 pieces here. There's going to be a pushing force from the ground and then a friction force. Okay, the pushing force from the ground is toward the chosen body. I'll call that N. And the friction force is going to be opposite the direction of motion. So that is, the magnitude is 0.1 times that normal force. And now we've dealt with the weight and we've dealt with every place the surroundings contact the boundary, so we know that's a complete free body diagram. Does this thing potentially have an acceleration along X or along Y? X. So we know our acceleration vector is A0. Okay, so now we're going to go to Newton's second law. What are the components of the weight force vector? It's in the negative y direction.
0, negative 19.62.
Yep, perfect. And what are the components of the normal force? That's in the positive y direction.
0, n.
Yep, exactly. What are the components of this friction force that's in the positive x direction? Exactly. Yep. The 5, this one's in the negative x direction. Yep, negative 5, 0. And then the last one is the 1 Newton force. That's in the negative y direction.
0, negative 1.
Yep, 0, negative 1. Exactly. And now these are equal to the mass, 2, times the acceleration that we already figured out is A0. Okay, so how are we going to solve this? Well, we have an x equation that says 0 plus 0 plus 0.1 n minus 5 plus 0 is equal to 2a. Or if we simplify this, it says 0.1 n minus 5 is equal to 2a.
Do we have to solve 5 first?
Yeah, that's exactly right. So this x equation, in the 2 examples before this, we've been able to solve for the variable right away, but here notice that this x equation has two variables in only one equation, so we can't solve it yet. So what we're going to have to do is go to the y equation, use that to calculate n, and then plug that back into the x equation. So the y equation says negative 19.62 plus n plus 0 plus 0 minus 1 is equal to 2 times 0. And so negative 19.62 plus n minus 1 is equal to 0. Solve the algebra and you get that n is equal to 20.62. And now we can take this and plug it into the x equation. So we have 0.1 times what we just figured out for n, minus 5 is equal to 2a. And so 2.06, that's not a 6, 2.06 minus 5 is equal to 2a. So 2.94 negative is equal to 2a. So a is equal to negative 1.47 meters per second squared. Yep.
Did you figure it out, Newton or normal,
The
the
normal force?
normal force? Don't you have to put newtons behind the 20?
Yeah. I was just going to wait until the end, to put the units on. That's what I usually do. Actually, I'll leave it off here. So, because these two things are going to go a long way towards telling us the answers to the questions. But now we have to go back up towards the questions and figure out specifically what we're being asked for. Okay. So for part A, we were trying to figure out the acceleration, okay, as a vector. We know that the acceleration vector is a0. Now we know what a is, so we can plug a in here to give the answer. So the acceleration vector is negative 1.470 meters per second squared. Or another way to think of that is it has a magnitude of 1.47 in the negative x direction. So it's this way at 1.47 meters per second squared. And then so this is for part A. For part B, we want to know the total force applied to the block by the ground. Okay, well, that's made up of two parts in a friction problem. That is the pushing force from the ground, and it's also the normal force to the ground, normal force from the ground to the object. Okay. We have what n is, so now we can just plug n into those two things. This was the acceleration. And so the force on the block by the ground is equal to 0n plus 0.1 times n, 0. And so that is 2.06, 20.62. That one's a little harder to visualize because it has two components. But if you wanted to get a sense of what that looked like, you could plot out that point. So go over 2.06, go up 20.62. And so that force vector is like in this direction. Okay, let me give a couple of problems and you can try to work through them. So the first one, let's say we have a cart with a mass of 3 kilograms, and we're applying a downward force of 10 newtons and a force to the left of 20 newtons. And let's say we want to calculate the acceleration vector. And second, the force on the wheels. You know, this is a force vector. Force vector on the wheels by the ground. Okay, so the first step is to draw the free body diagram. Take a couple minutes and see if you can draw a free body diagram for this. And at each one of these steps, then I'll go through it so you can make sure you're thinking about everything right. All right, so there's the outline. There's a weight force of 3 times 9.81, so 29.43. There's a downward force of 10 and a force to the left of 20. And then there's contact with the wheels. That's a pushing force, so that force is toward the body, perpendicular to the surface, and I'll call that N. Okay, so there's the free body diagram. The next step is, what do you know about the acceleration? Is this thing going to move along X or along Y? X, yep, so we know that the acceleration vector we're going to represent as A0. And now the next step is to put all of this into Newton's second law. To do that, you need to come up with the vector components of these forces. So take a couple minutes and see if you can format Newton's second law with this stuff, okay? Okay. So Newton's second law, the weight force is in the negative y direction. The normal force is in the positive y direction. The 20 Newton force is in the negative x direction. The 10 Newton force is in the negative y direction. 1, 2, 3, 4, 1, 2, 3, 4, so I have all the forces in there. And now these are equal to the mass, 3. times what we figured out was the acceleration vector, a0. Okay, so the next step is break this up into the x and y equations and solve for the variables. So take a couple seconds and do that. Okay, so we have the x equation says 0 plus 0 minus 20 plus 0 is equal to 3a. And so a is equal to, that should be negative 6.6 repeating, I think. And the y equation says negative 29.43 plus n minus 10 is equal to 3 times 0. And so n is equal to positive 39.43. Okay, there's one more step. Now we've solved for the variables. Now go back and put these into the vector forms. So find the acceleration vector and the force vector applied to the wheels by the ground.